Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New City Western, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UE, St. Augustine.
Mistakes are very common in the equations of mathematical physics. Back in mid-1981 and in a physics research seminar at College Park, Maryland, I was laughed at and dismissed as a crank when I pointed out that the physicist Enrico Fermi had incorrectly stated the equations in his widely reprinted blackboard photo. The representation of that photo of Enrico Fermi was reprinted on both the Italian and the United States postage stamps. Enrico Fermi was nicknamed, quote unquote, the Pope, because it was alleged that he never made mathematical mistakes. I had the last laugh when those research physicists discovered that I was right and that Enrico Fermi was wrong. Back in the early 1980s, and in a physics research seminar at College Park, Maryland, I was laughed at and dismissed as a crank when I pointed out that Albert Einstein did not invent the equation E equals mc squared, and that Albert Einstein incorrectly rederived the equation E equals mc squared. I had the last laugh when those research physicists discovered that I was right and that Albert Einstein was wrong. My contributions to calculus is this: I correctly derived the partial differential equation of calculus that is used by the petroleum industry, and I correctly classified them as hyperbolic, and I did so when the calculus textbooks incorrectly classified them as parabolic. The partial differential equation is the most advanced expression in calculus and the most important equation in mathematics. As a research mathematical physicist, I discovered that the reason the partial differential equation of petroleum geology was parabolic instead of hyperbolic, as I theorized, was that only three forces, namely pressure, viscous, and gravitational forces, were summed up when summing up the forces used to derive those partial differential equations. As a research physicist that was at the frontier of knowledge of fluid dynamics, I knew that four physical forces govern the motions of water above the surface of the earth, such as in rivers, lakes, and oceans, and govern the motions of air and moisture in the Earth's atmosphere. I also knew that those same four physical forces govern the subterranean motions of fluids below the surface of the Earth, such as oil, water, and natural gas, flowing from water injection wells to oil and gas production wells. I discovered that the fourth force, the temporal and the convective inertial forces were missing in textbooks on porous media flow and that were used by the petroleum industry. After I corrected the mathematical errors, the governing partial differential equations became hyperbolic. I corrected the mathematical errors by accounting for the missing inertial forces. And for the first time in porous media flow modeling, F is equal to MA, or the sum of the forces is equal to the product of mass times acceleration. The introductory textbook on how to solve partial differential equations of calculus uses the classic heat equation of physics as analytical and computational test beds. For that reason, I also used the heat equation as my analytical and computational test beds. The reason I used the heat equation is that it is parabolic. The mathematical structure of the system of coupled nonlinear and time-dependent partial differential equations that governs the multi-phase flows of oil, water, and natural gas flowing through a porous medium is also parabolic. Consider the two-dimensional heat equation and the grand challenge of solving it across a small copy of the internet and solving it in the 1970s and 80s when it was believed to be impossible to parallel process. Imagine that small internet as a global network of 65,536 commodity processors that are identical to each other and that are equal distances afar and apart. Consider the grand challenge of solving that initial boundary value problem that was governed by the heat equation and solving the problem 65,536 times faster than is possible to solve on only one processor that is not a member of an ensemble of processors. Back in the 1970s and 80s, I was warned that parallel processing is a huge waste of everybody's time, and I was warned that it will forever remain impossible to solve the heat equation and solve it across my small internet. I was warned that, according to Amdahl's law of parallel processing, that it will be impossible for me to achieve an 8-fold speedup and achieve that speedup across an ensemble of 8 processors. The heat equation, when restated in prose, instead of in its native calculus, had the partial of temperature with respect to time to be equal to the product of kappa and the sum of the second partial of temperature with respect to x and the second partial of temperature with respect to y. The heat equation, as I described it, has one dependent variable and 3 independent variables. As a large-scale computational mathematician, I devoted a good part of the early 1980s doing theoretical stability analysis of finite difference algebraic approximations of the heat equations, as well as the stability analysis of its cousin of the opposite sex, known as the wave equation.
Insightful and brilliant lecture.